What is up, IM1 Nation? In this episode, we'll be talking about area. Area, I hope, is something that we've already been familiar with. It is the space inside a shape, and we're going to look at how to turn that into something more abstract. So let's go ahead and get started by turning to your page 17. Let's go ahead and... What I want to find out here for number 1 on page 17 is what is the area of this figure right here. Here we have this giant, massive square that takes all this space, and each little square, I tell you, represents 1 square centimeter. So we have 1 square centimeter right here, all the way across, all the way across, all the way across. And there's 2 ways you can find out what the area is. One is the simple and easy way, which is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The area is 16 square centimeters just by counting it. But the faster way of doing this is looking at what is the length and the width of this rectangle. Hopefully you all remember that the area for length times, the area is equal to length times width. So what I've got here is that I have the length. It has a width of 4 squares. And then I have a width. It is a length of 1, 2, 3, 4. 4 squares also. I can get 4 times 4, which I'm going to find out is equal to 16 still. So it doesn't matter what method I choose. If I multiply the sides of the square or count the inside squares of the bigger one, I'm going to end up with 16. Looking at this next one, number 3, I don't want to count all these squares. So here I can totally just count them one by one, but I want to do it the smart way, which is looking at what is my width. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 centimeters is my width. What is my length? It is 1, 2, 3, 4. Area is going to be equal to 4 centimeters times 9 centimeters. Combine those together, my area is going to be 36 centimeters squared. And I can get that same answer if I counted literally every single square, but I don't want to do that. For number 5, if I really wanted to, I can use my pencil and literally draw out rows of 8. Why would I do that when I'm already told what the length and what the width is? Here I have 3 and 8. So my area, doing things a lot faster, would be 3 centimeters times 8 centimeters, which would give me 24 square centimeters. Problems 6, 7, and 8 are a bit more challenging than this, however. Your task on these problems is to use this drawing to split it up into different rectangles that you can find the areas of. Let me go ahead and help you out with number 7. Number 7, I have this long piece over here on the right, which is equal to 7 centimeters. And that's going to be the exact same as this part right here on the right. I have 4 centimeters plus another 3 centimeters. 4 plus 3, I hope we all know, is equal to 7. Over here, though, things get a little more complicated. I have this long piece on top that's equal to 10 centimeters. And this really short piece that's in the bottom that's equal to 5 centimeters. So if I want to find out what that missing side here over here is on the left, well, if I know the whole thing is 10, and this little piece here is 5, then this remaining piece right here has to be 5 centimeters also. And then from there, you have 2 options. I'm going to show you one of them. I'm going to go ahead and cut this weird L shape into 2 rectangles that go off like this. I want to find out what is the area of this first rectangle. I'm going to shade in orange over here on the right. Well, I know the length is 5 and the width is 7. My area of this bigger rectangle is going to be 5 times 7. So 35 centimeters squared. The area of this smaller rectangle, well, I don't care about the 10 centimeters because I've already split it up into this 5 centimeter up here and that 5 centimeter down there. So what is the area of this rectangle? I'm going to shade in pink on the left. 5 times 15 will end up being 15 squared centimeters. And the area of this L shape in total, 50 square centimeters. Moving on to page 18. This one's a bit more involved, but I promised you it is nothing too different. Looking at this rectangle drawing over here, I know that the dimensions of this square, it has a length of x and a width of x also. If I knew what x was, if it was, for example, 5 and 5, the area would just be 5 times 5, so 25 in the middle. If this area was 9 and 9, I would know the area is just 9 times 9. But because I don't know what this x is, x is a number, I just don't know what that is. That's totally fine, because I know that x times x, recalling our information from chapter 8, x times x is going to be equal to x squared, x to the power of 2. Similar thing here for this rectangle on the right. I know the length is 1 and the width is x. So the area of this rectangle is going to be 1 times x. 1x. Same thing here for this rectangle in the bottom left. Because this length up here is equal to x, this length down here is also going to be equal to x. There's no reason why it wouldn't be. It's going to be the exact same in the top here as it is in the bottom there. Lastly, I have this bottom right square. I know that this top side has a length of 1 and this left side has a width of 1. The area is going to be 1 times 1. In other words, 1. What I want to go ahead and do here is I am going to find out what the area is of this mystery square in 2 ways. The first one is the first way I suggested on page 17, which is literally adding up the area of everything you see inside that big square. So to do things this method, it would be x to the power of 2, x squared, just like that, plus this x over here, plus this x in the bottom right, plus this one little square that has an area of 1. That's the only number that we have. These x's in the middle will combine, and then we have x squared plus 2x plus 1. We do not know what x is. If we knew what it was, we can replace x in this long little expression that I have with like 5 in parentheses, for example, if x was 5, and then put it into our calculator and then find out what the area actually is. But because we don't know what it is, let's leave it as x. Another way I can find out what the area is doing the length times the width we did a while ago. I'm going to shade my length in orange and my width in pink. So here what I've got going is this. I promise you're not missing anything when I do this. The length of this top side of the square is just x plus a little bit more, plus this little bit that's 1. So if I want to know what the length of this entire top side is, it's this mystery side plus the 1. If I want to know what my width is, it's going to be the exact same thing. I have this length or this width right here that I don't really know what the size is, but whatever that is, I am adding one more little bit to it. So here, I've got x plus 1 as my width and x plus 1 as my length. In parentheses, do x plus 1, and then parentheses again, x plus 1. Put a box around it. This is my length, this is my width. They just happen to be the same thing. Looking over here, I once again do not know what the length of this side right here is. It's just x. In the meantime, the area of this square at the top left is going to be x squared, x times x. The area of this rectangle over here in the top middle is going to be 1 times x. In other words, just 1x. Same thing over here. 1 times x is still, 1x. Doing that same coloring I did for number 9, I have this side up here that has a length of x. So this bottom side is going to have the exact same length. There's no reason why it's going to be different. 1 times x is going to be equal to x again. That's the area of that rectangle. And here's the shortcut I want you to kind of figure out by now. All these rectangles are going to have an area of x. These big squares will always have an area of x squared, and these little squares will have an area of 1. Let me go ahead and write out the area by adding everything inside the gray squares and rectangles. X squared, I use this one up, plus x again, plus another x, and then I have a 1 plus another 1. Put a box around that, get a stamp. Let's go ahead and look at the length of this top rectangle here. 1 plus 1, I hope we all know, is 2. So when I write down my area, my length is just going to be parentheses x plus 2. Now let's find out what the width is. My width for this side of this overall giant gray rectangle is going to be x plus 1. Put a square around it. And one thing you can totally do is write an equal sign. A really long one. I should have done this a little better, but equal signs. What you've got here on the middle column of your page is the exact same thing as the thing on the right side of the column. When you go to number 12, you're working your way backwards. I let you know that the rectangles are x's. This big square in the bottom left is x squared. And these little ones, I hope we all know, based on what I said earlier, will have an area of 1. When I write out my area by adding up everything I have, I'm going to have 1x squared. Let's go ahead and skip some steps already. I have 1, 2, 3, 4, 5, 6. I'm going to have 6 x's. How many little 1 squares do I have? Looks like I have 1, 2, 3, 4, 5, 6, 7, 8. Put a box around that. I want you to know that the lengths of these rectangles that have an x have a length of x, and they have a width of 1. Go ahead and fill this in, the rest of the perimeter. That's another word I hope you know. If I want to write out my area as length times width, you could write the width, if you like, as 2 plus x. It does look like it'll be 2 plus x because you have the 2 first and then the x. I would rather, though, we have the x's first. But really, it does not matter. This is just Lopez prefers. Much like how I prefer the simplest slope when calculating slope, I think this just looks nicer. When you get to page 19, these big squares have a length or area of x squared. These rectangles have a length of x all the way through. For 3-85, the area as the sum of all the gray shapes, and then make that equal to the area as the product of length times width. That's all I have for you today. I will see you on Monday.